This is lesson 10 on phase change diagrams, which is a Regents and Honors topic. We're going to be reviewing the different phase changes that matter can undergo, and we're going to be talking about two very special locations on phase change diagrams that we need to know. So when we talk about phase changes, we understand that when a solid melts, it turns into a liquid, or when a liquid vaporizes or boils, it turns into a gas. And gases, if they happen to, can condensate and turn back into liquids. That would be removing heat from them.
Liquids can be solidified to or frozen to make solids. Solids can be sublimated to make gases. Gases can deposit to make solids.
So a phase diagram is literally just the graph with the x and y axis that give you temperature and pressure at which any substance can be in either the solid, liquid, or gas phase. The different temperatures and pressure will then direct you if that sample is solid, liquid, or gas. The conditions of pressure and temperature at which two phases exist at the same time is what we call equilibrium. Equilibrium is indicated on the phase diagram by all of the lines that separate the different phases. Let's look at a phase change diagram. So, our y-axis is pressure in kilopascals. Our temperature is Celsius. We're also noticing a bunch of dark lines. Those lines are equilibrium. So for example, if you looked at a temperature and a pressure and you fall on that line, that means your sample is in a phase change. It means it's going from one thing to the other. Now you're noticing that there are three different points on here. We have a triple point, we have a normal melting point, and a normal boiling point. So the first point that was on the graph that we just went down to is called the triple point. And a triple point is a very specific condition. And everything that occurs on a triple point is in a closed system, which means nothing can come in and nothing can leave. A triple point is the phase at which liquid, gas, and solid can exist in unison or in equilibrium with one another.
All 6 of those phase changes are actually occurring at the triple point.
The other point that's incredibly important is what we call the critical point, which is a point on the phase diagram at which a substance is neither completely liquid nor completely gas. It exhibits properties of both the liquid phase and the gas phase, which we call a supercritical fluid.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
So it may look like a liquid, but the molecules are spaced so far apart that it exhibits properties of a gas. A lot of supercritical fluids, for example helium, have the unique ability to basically diffuse or effuse straight through a container that's holding it, which means the liquid will go right through its container and then vaporize on the other side.
Critical temperature is the temperature at which the critical point exists, and critical pressure is the pressure at which the critical point can exist. So when we look back at this phase diagram, and this one's for water, you'll see that at the critical point, we have a pressure and we have a temperature. Again, that's the critical pressure and the critical temperature. Water becomes a supercritical fluid at approximately 22,000 kilopascals when the temperature is held at 374 degrees Celsius.